So this is my last idea about cohomological sets, chaotic sets of cohomologies, I'm calling them, within game theory. I'll try to point the camera more at what I'm talking about, unlike the last video. So this is what I was explaining to you in terms of game trees over here, or game trees over here. It's just like, you can literally think of them like bifurcating trees. The point is, they go by the rules of what's called the payoff matrix. So you have P1, P2, there's some kind of payoff matrix, like in this one, these are negative 2's. If they do this, the probability of payoff for this person is 6, and for this person is 6. For both of these it's 1 here, for both of these it's 6 here. So everyone they'll try to optimize and get this result. It's improbable, so more than likely these two it's going to be the actual result. But because they chose this is the actual outcome. And then you can kind of get the prisoner's dilemma version of this, but the real crux of it is that there's n choose r possible versions of whatever combination of like operators exist within the variables that determine the payoff. So it could be a and b, which is like I'm defining as a set within n of n choose r, can be equal, which means like they could be equal like this, or one could be less than the other one, or one could be greater than the other one. So that's just how I kind of wrote it here. And then the point of this is that every time you play the game, it's like going a step in one of these trees. So these are decisions essentially in the game, and you can play the game multiple times. And so there's this thing called optimal strategy or dominant strategy, which is basically saying that every single time they're going to be going for these, and therefore the result is some average of these two. That's not actually the best optimal strategy for both players together, which is kind of like the cohomology. Locally, they can have a dominant strategy, but there's a cohomology called the Nash equilibrium. So there's this guy called John Nash, who is a super genius in mathematics, who found that there was problems in the laws governing economics and game theory that didn't consider this principle, which was that the thing that if every player doesn't act in their own self-interest, but in their self-interest and the interest of the group, then they'll reach a Nash equilibrium. The problem for Nash equilibriums is that there has to be a dominant strategy, which I denoted as d sub n pi, which means for the ith player, there's an nth decision that is dominant, but there has to be a dominant decision for each player, and they have to be consistent. So that would allow you to have a Nash equilibrium, but it could be that either neither one of the players or none of the players have a dominant strategy, or that the dominant strategy isn't consistent or equal for all of the players. So kind of the chess analogy that Feynman goes through is based off of a system or a game system where the entire tree is known at every time that you make a move. And so in chess, you make a chess move, and they kind of like, this would be like a board position here, entire board position. And then this is if you make this move, but in chess, the possible amount of moves isn't 2. Like there's not just 2 decisions, like in this game, there's many. So each of these wouldn't bifurcate. It would frigate or whatever by the amount of decisions that are possible in that state for the system. But we still can determine all those possible moves, and then therefore we know that the amount of moves for a chess game is finite, even though it's dynamically evolving. But for a chaotic system, it can be kind of weird. So that's the whole point of the chaotic set of cohomologies. The cohomology would be like a Nash equilibrium. So if you're trying to find Nash equilibrium, and you're working off of some complex function. The Nash equilibrium being some kind of decision, which I've defined here as it is the decision that most maximizes symmetry in whatever next step in the position of the geometry is defining the position of information on the surface of the black hole that we were talking about in the last video. So the nth players, or the players in this situation, would be zeta functions or complex functions. So in this case, any move, which is a small change in position on this graph towards the outer horizon defining the divergent space, would make, just an example, would make, there's an nth amounts of players, or there's a ton of players, and they can make obviously more than just two decisions, so I just represented that by random lines. But the point is, this is one state, and so let's say this defines actually the entire, like in the chess game, the entire infinite, not finite amount of possible ways that they could have moved the chess pieces, and then how those games could have evolved completely, depending on how many, and these are more like they're more like positions, I guess. Check this real quick. So these are more like positions, and these are more like players to the piece of n making a move in each of these positions. But this entire matrix would be a game. And the problem is that it's not clear that every time you make a move with these positions, with the amount of players within this is position, and these are the players, that the finite set of decisions in that game tree is consistent. You don't even know if you have the same amount of players, you don't know if you have the same amount of possible positions anymore. So the game trees might look completely different every time you make a move. And that would just keep happening. And the rules for how they would change would seem chaotic. And that's because they're trying to keep track of that cohomology thing. So it could be that some states don't have Nash equilibriums or successful methods for cohomology, reconciling the consistency of a cohomology. So you look at this triangle, it's the same thing as like if I cover one area, now it makes sense. But if you look at all three areas, it's like an impossible shape, at least in terms of the dimensions that we think of. So it's just another example like of a checkerboard, and how there's a finite amount of positions, and how each of these are two possible moves in that position. But obviously there's more possible moves that they could have made at that time, and then those have more possible moves. So, and then each time you make a move, there might be more moves, but it's still finite. Whereas in this case, it may be finite, but it's finite in an unpredictable way. So it's chaotic, and that's kind of the whole point. In this case, it's determined. So there's a progression. After you make one move, then you can make 4 moves, and then it's possible to make 4 moves for many different positions, and eventually you can make one of 5 moves, and then 6 moves or whatever. So the point of all this is that this whole system that I was talking about before, where you have these locally consistent systems that might have Nash equilibriums, there may not be a way to make this whole system a Nash equilibrium. And the whole idea of the Huerta puzzles is that the complexity of the system has this upper limit of least action that trends towards making this one local region until the entire black hole is essentially a local region that has a Nash equilibrium, which is essentially just a reconciliation of the consistency of cohomologies as they're made up of decisions to maximize symmetries. Tried to make it shorter, but I think it's still going to have to go to YouTube. I don't think it'll fit on text.